All right, folks, here we are. Welcome to my zero-budget basement film studio. We will learn together from the comfort of my basement. I hope everybody out there is doing well, staying safe, chatting with your grandma every day. We're going to try and make the best of the situation here. So what my plan is, what I would have done in class, I'm going to instead do on these here videos, and you shall watch and learn. I hope that you are able to treat this, video watching experience much the same way that you would as if you were sitting in class. For instance, I think you should take notes just the same way that you usually would. You can watch the video over and over again whenever you want. But I think probably you will still learn better if you write things down the way that you usually do. I wish it didn't have to be this way. I wish I could see your faces, but that's fine. I suppose we'll do just fine without the faces. One thing that is unfortunately a bit of a pain, I had a handout for today that I was going to hand out and have you all draw on. So you will see a link in the video description or on the class website where you can get the handout. You will want to be able to draw on the handout. If you have something like an iPad with a pencil or something, then that'll do just fine. Otherwise, you probably will want to print it out. Sorry for any inconvenience about that, but that's the way it is. If you were here, I would print it for you. All right, let's get started. We are still talking about gerrymandering. We have two more topics left to discuss concerning gerrymandering. We are on the general topic of how can one evaluate and detect gerrymandering. If you look at a district, how can you tell if there has been some kind of unfairness going on in the way the district is drawn? The first thing, and the only thing on this topic that we've discussed so far, is the efficiency gap. That is a way of sort of counting up all the voters in each district and seeing, measuring the amount of wasted votes, right? We are going to talk about two more methods for evaluating how fair the districts are, and these ones are purely geometric. As you know, here's a basic principle which we are all familiar with by now. Unfair districts tend to have weird shapes, right? You've seen that, and you know in order to achieve weird outcomes, the shapes sometimes end up being very weird. So one way that you could think of measuring gerrymandering would be you don't even have to look at where the voters live, where the Democrats and Republicans live, and count all the wasted votes, whatever. Maybe you could just look purely at the shapes, all right? Don't even think about who's voting for who in this district or whatever. Just look at the shape. If the shape is really weird, then probably something bad is going on. If the shape is normal, then probably it's fine. So we are just going to look at the shape. So we're going to talk about two different, what I will call geometric measures of, I'll put this in quotes, weirdness of shapes, right? When you look at a shape, there's some kind of gut reaction that you have. You look at a shape and say, yeah, that one looks pretty weird, or this one does not look pretty weird. But really, if you're going to make a big deal out of this in the real world, which is what we're talking about here, you need to have some kind of actual specific measurement that you can make, which will tell you, which will try to measure how weird the shape is. And for just as a simple example, the kind of shape which should seem not so weird would be, something like that. This you should feel like is not very weird. Whereas something like this, right? Something like that. This is very weird. All right. So our goal for this little section is going to be to talk about two different very specific ways you could use, and then you could actually look at these two shapes in these two different ways and measure how weird is the shape. All right. This is likely something that you've never talked about in your math classes, but there is such a thing as a specific way of measuring a shape to determine how weird it is. You want sort of a nice shape is something that is more like sort of a single blob, maybe close to a circle or a square or something. And a weird shape is one that's like a big wormy kind of thing. All right. Anyway, we're going to talk about two different ways. Let's do the first one. Both of these two different ways, they have fun, weird names. The first one that I want to talk about is called the Convex Hull ratio. There shouldn't be a dash there. The Convex Hull ratio. All right. So when we, actually talk about the definition here, what you're going to end up with when you do the convex hull ratio, you start with a shape and you want to tell if it's weird or not. The convex hull ratio ends up being a fraction, and if that fraction is close to 1, then that's a nice shape, and something close to 0 indicates a super weird shape. All right, so the convex hull ratio is going to end up being just a specific number as the answer, and it tells you how weird the shape is, where 1 is like perfectly nice shape, and close to 0 would be an insane, wormy kind of shape. All right, let's talk about how we do it. So here, let's just start with a little basic geometry. This word convex, maybe you've seen this before in if you had some kind of geometry class. Convex. This is a mathematical word here. Convex means this is a property that certain shapes have. Some shapes are convex. Some shapes are not convex. The word convex means if the straight line connecting any 2 points in the shape lies entirely within the shape. This is kind of hard to understand what I mean. I'm going to write it first. Entirely within the shape. Come on now. All right. Convex means if the straight line connecting any 2 points inside the shape lies entirely within the shape. I mean, you take any 2 points, you draw the line between them, the straight line connecting them, and that whole straight line has to still lie inside the shape. If that's true for any pair of points, it's called convex. The classic example of this would be something like a circle. This is convex. Because if you take any 2 points in the circle, say here and here, draw the line connecting them, the whole line is inside the circle. All right, that's what it means to be convex. No matter what points you take, I could take 2 points right here. They can be on the edge if you want, it doesn't matter. Draw the line connecting them, and the whole line is still inside the circle. All right, this is also true of most it's true of all regular polygons. For instance, a triangle is convex. Because, again, if I take any 2 points in the triangle, they could be on the border or just anywhere on the inside. The line between those 2 points is inside the triangle. All right, so this one also is convex. How about some that are not convex? Here's one that's not convex. How about something like a Pac-Man? All right, this is like a circle that has a wedge cut out of it. Not convex. Do you see why? If it's not convex, that means there must be some pair of 2 points where when you draw the line between them, that line must leave the shape. And in this case, this Pac-Man, if you take, say, a point up here and a point down here, and you draw the straight line between them, then this line is not entirely contained within the shape, right? Because this part of it here sort of goes outside. And so this is not convex because there are some points where you can draw the line between those 2 points and the line will leave the shape. That means it is not convex. All right, how about some others? What about something like, this is very similar, but how about if I do something like that? Isn't that cute? Convex or not convex? The answer is not convex because there are, just like the Pac-Man here, there are ways that you can choose 2 points. There are many ways you could do this, but, you know, specifically something like that. These 2 points, the straight line connecting them leaves the shape, and so this is also not convex. All right. Basically, not convex means there's some kind of like an innie part of the shape, right? This, you know, there's the fact that there's this like inwards coming absence in the shape, the innie, that makes it not convex. How about this? Let's make another shape. How about a little hand, right? I could draw around my hand. Wouldn't that be cute? What do you say, convex or not? The answer is not convex. There are many kind of these innie kind of areas in between these fingers, right? I can take 2 points like that, and the straight line here must leave the shape. In fact, there's even a non-convex portion right here, right? You see this part? I can take a point, say there, and another point over here, and the line connecting those 2 points, again, will leave the shape. All right, this one is not convex. You get the idea? I hope you get the idea of what it means to be convex versus not convex. Convex basically means there's no innies in the shape, whereas not convex means there are innies in the shape. All right? What if you just consider a random shape in the real world? Typically, shapes, just if you make up a weird shape, it's usually not convex. Like this one I drew has this little non-convex portion right there, or there's one up here also. Right? If you just at random draw a shape, it's probably not going to be convex. Okay, are we clear with what is and is not convex? I hope so. All right, this method of gerrymander detection is it's called the Convex Hull ratio. Let's talk about what that means, the Convex Hull. Like I said a moment ago, a typical shape that you encounter if you just sort of draw some kind of wiggly shape at random is generally not going to be convex. Let's maybe something like how about that? Nice little flower. Is this convex or not? It is definitely not because of all these sort of innie parts that make it not convex. The convex hull is a way of taking a set to begin with, which is not necessarily convex, and adding some stuff like filling in all the innies to make it a convex set. So if we begin with this set, this is, let's say, the original set. I'm going to draw with another color here what the convex hull is. So, got to shake it. Let me just say, I'll write sort of in words what the convex hull is. The convex hull is the shape. I gotta press down, down, down. That is no better. Can you read that? I hope so. Come on. The convex hull is the shape obtained by filling in all the non-convex parts. Fill in all the innie parts of the shape, right? So, for example, right here, all of this stuff in here, that is not part of the original shape. If you want to get the convex hull, you got to fill that part in. So, the convex hull I'm going to draw, it involves the entire original shape is part of the convex hull. Plus, I'm also going to add in, now to fill in this entire innie part, really you need to join there to there and then fill all of this in. And of course, I'm also going to fill in the entire interior of the original shape, all right? But I also take that bit there. And then you got to do this all the way around, of course. So there's also an any part here. You have to look on the whole shape and find every one of those sort of inlets and fill them all in. So this part, I need to fill this in. So I also take that. This part, I fill that in. Over here, I also fill this in. And then this one down here. Now, actually, if you look very closely at my picture, you'll see I need to fill. That should be a straight line. I didn't mean for it to wiggle like that. Ooh, look at that. Not great. Like so. All right. And so in this example, the original set, let me just, maybe hard to see at this point because I scribbled on it. The original set looked something like this. And then the convex hull looks like it's vaguely like a pentagon. It's that whole thing that surrounds the whole thing. I'll draw it over here. Sorry, I don't have a lot of room on this little fabulous setup. Right, the convex hull is this entire blue area here, whereas the original set was only this little, starfish kind of thing. All right, this is the convex hull. I thought we should just draw a few more examples. So when you are finding the convex hull ratio of a gerrymandered district, you need to draw this picture over and over again. So you have to become very comfortable at, if I have a picture for you, can you draw me a picture of the convex hull? It involves just sort of filling in all these inny regions of the shapes. How about the old Pac-Man? What is the convex hull of this? This is not convex because of this inny thing. How do we have to fill it in? And the way to fill it in this case would be to just join a straight line like so. And then everything in here would be the convex hull. So when you're finding the convex hull, if you start with the Pac-Man, the convex hull is... it's not quite a circle because this part here really, all you need, if you put a circular arc here, you're taking more than you need. The convex hull is supposed to take only the smallest amount to fill in all of the inny regions. So I'm going to take a straight line so it looks like almost like a circle, but it has sort of a straight part here, which is where the jaws of the Pac-Man used to be. All right, if you start with this shape, the convex hull would be that shape right there. How about, I just have another simple few examples here. What if I had a nice looking heart? How about that? This one, if I were to draw the convex hull, you got to look at this picture and say, what do I have to fill in? Where are the inny parts? What do you think? Think about it. I hope that you thought, well, the top here of the heart is kind of an inny part. That's actually not the only part that you need to fill in. I can see two other regions that need to be filled in. Do you see the two other parts? They are actually here and here. There's this sort of arc going inwards and a similar one over there. So the convex hull of that heart, if I were to write, let me just copy the original heart again, it would be connected up there and then also requires some lines here and here. All right, and you get this. You can scribble it in if you want or just draw the outline, whatever. It's not going to be confusing either way. Okay, this is the convex hull of that heart. I had two more quick examples. How about that? And how about this? Convex hull of this, it's like a capital E, right? We have to fill in all the innies. Actually, there's a huge region of this shape which needs to be filled in. This entire sort of thing, all of that space is like one giant inwards intruding thing, right? I keep saying inny. Does that seem stupid of me to use the word inny? I hope you don't mind. I know it sounds stupid. Anyway, all of that business needs to be filled in to get the convex hull. So actually the convex hull of that is really just a rectangle, right? You would end up just connecting that part to fill in this entire region there, and you end up with that. All right? Sometimes you might mess things up and like not fill in enough, but you'll always end up with this shape if you can continually fill in. Like for instance, if you didn't realize you had to connect the top end to the bottom end, what if instead you said I need to connect that and then that, right? You could fill this part in and then also fill this part in. But then you will realize that you still have another innie here. Like you haven't fully filled this thing in. Then you would decide to finally connect these up and then get the whole thing. You'd end up with what I got eventually. Right? Keep on adding parts in until there are no innies anymore, and you've filled everything in. All right, how about this? This one actually, you don't get the rectangle. In order to fill in all the innies, you might fill in that one first, but then there's also kind of this, and there's also this, and then even if I filled that all in, there's this right there. I think once you get that much, then you have filled in everything. So the convex hull of this is a weird looking shape like that, right? We have filled in, taken this diagonal from that point all the way down to this point. This is the convex hull. All right. I hope this seems doable. This is why, by the way, I said you're going to want to print out this handout so that you can scribble on it, because I have a bunch of examples that I wanted you all to try out of finding the convex hull. So what I would like you to do is check out the first handout. I'll show it on the screen here so that you know what I'm talking about. And I would like you, for each of those shapes, you can just draw right on top of it. Draw the convex hull. How about this? I'll do the first one with you, and then I want you guys to try all the rest of them. Okay, I got my handout. Our job for each of these weird shapes is to draw the convex hull, and I'm just going to scribble it right on top of the existing shape. So for this one, we already did one like this. We have to fill in the top bit there. And we also have to fill in this part over here. And then this actually looks pretty straight as is. Maybe I'll fill that in. All right, the rest of these curves can just exist as they are. And then if you want to scribble in, that's the convex hull of that one. All right. Some of these, as you're doing, I want you to try these on your own. Some of these you will notice that maybe they are already convex. Then the convex hull is just the same as the original shape. So if the shape on the page is already convex, then you don't have to do anything, or you can just say the convex hull is the same as the original shape. All right, will you give it a few moments and see if you can try these? I'm gonna direct you to pause your video, see if you can draw the convex hull of each of these, and then I'll come back in a moment and see how you did. All right, I hope that went all right. Let's just go through these real quick. So the star here, I hope you connected sort of these tippy tips. And then the result is sort of a pentagon thing, all right? How about this one, this strange wormy thing? In order to fill in, there's sort of this big region here you need to fill in, so I'm going to make a line like that. And then there's also this region over here you need to fill in. And I'm going to have to connect from here all the way down to there, okay? The rest of it, this part here, doesn't need any modifications because there's no innie, right? So it's this whole region right there if you want to fill it in. All right? Let's go to the next one. How about this? This is a weird shape. Looks kind of like a hand, I guess. I don't know. Fill that in right there. And then these fingers have to be joined up with a straight line. And then otherwise, I think it's just this shape, right? For this is kind of like a little house. I would connect there and also there. And otherwise, everything else we can take. There's no other innie parts. So this, I guess, is that a pentagon? Yeah, that's a pentagon once you fill in those lines. All right. The circle, this is already convex, so you don't have to change the shape at all. It's just the exact same shape is the convex hull. There's no parts to fill in. All right. How about this one? We did one like this earlier. This is kind of like the Pac-Man. You need to fill in everything in here. So that's the convex hull of that one. And then finally, oh no, the triangle. This one is convex already. We already said that a triangle, any regular polygon, is convex. And how about this wormy thing? It has a nice, cute little face on it. That's just because when I drew it, I my pencil slipped and I got this extra, that little curly thing was from my pencil originally, and then I decided to draw a nice little happy face. Anyway, this thing, where's the innie parts that you need to fill in? It's this whole bit right here is a big innie part, so you need to connect with a straight line all the way like that, and then the rest of it is the convex hull. All right, just ignore the face on there. Okay, so I hope these are the shapes that you got. Those are the shapes that I got. All right, I'm ready to talk about the convex hull ratio. Remember, this is that thing I said we were aiming for is a specific measurement which will tell you how weird the shape is, and it's based on looking at the shape and comparing it with the convex hull. And the basic idea, I will call this the CH ratio for convex hull. The basic idea is that a nice shape is pretty similar to its convex hull. What I mean by that is if you just sort of draw a, not like a perfect geometric kind of shape, but something that's not so weird, like this. This is not so weird. This shape is pretty close to its convex hull. If I were to draw the convex hull of this shape, I would have to fill in, say, this part. I'd have to fill in this part. And I don't know what that is, but maybe fill in something right there, right? But in this example, this shape and its convex hull are not very different, right? They involve this little thing, and this little thing. That's the only difference, though. Versus some kind of weird wormy shape, something like, say that. This shape is very different from its convex hull. For instance, the convex hull of this shape, I have to fill in this entire region here with a straight line, say like that, and then I also have this thing here which needs to be filled in. And I suppose it has to go all the way down to there, right? This is now, the convex hull contains all of this stuff, and the convex hull, in this case, is much bigger than the original shape. So a nice shape is pretty similar to its convex hull. A weird, wormy shape has the convex hull is much bigger than the original shape. So a weird, wormy shape has the convex hull, I'll just write CH, much bigger than the original shape. This is where the basic idea of using the convex hull in this context came from. It came from the realization that a weird, wormy shape is generally going to be very different from its own convex hull, whereas a nice kind of blobby shape is already very similar to its own convex hull. All right, let's talk about how do you actually make that number. The convex hull ratio is supposed to be a specific number that you get when you look at a shape and you compare the shape versus its convex hull. And really what we want to compare is the area of those two shapes. Remember I said in a weird shape, the convex hull is much bigger. What I mean by bigger is the area of the convex hull is much bigger than the area of the original shape. So that's what the ratio is going to look at. I'm just going to write, we'll just call it CH. This is sometimes called the convex hull score or the convex hull ratio. Anyway, the definition is, it's just a fraction. That's why it's called ratio. And the ratio is the area of the original shape divided by the area of the convex hull. All right. So in a normal shape, these two areas are almost equal to each other. They're very close to each other, which means this fraction will be close to 1. In an ordinary looking blobby shape, this fraction is close to 1. So for a nice shape, means that the convex hull score is close to 1. That's because this is a fraction in which the numerator and the denominator are close to each other. Whereas if the shape is some kind of wormy worm, then the bottom of this fraction will be much larger than the top, and so this fraction, its value will be close to 0. So a wormy shape will have the convex hull close to 0. And this is a real thing that you can really measure of a shape. The biggest obstacle to actually measuring this is just that it involves areas. And as you know from whatever geometry you learned in high school or wherever, finding the area of certain shapes is not so hard. Like you learned a formula for the area of a triangle, or the area of a rectangle is easy. There's something for the area of a circle, right? But how do you find the area of just some weird wormy shape? That actually is not easy at all. So what makes this difficult to find is areas. This is a basic fact. Areas are hard to measure sometimes. Unfortunately, to find the actual area of something is difficult if it's some weird wormy shape. Like, do you know the formula for the area of a weird wormy shape? The answer is no, there isn't a formula for the area of just some random wormy shape. It does have an area, but there isn't a nice formula for it. It actually, I don't know if you care about this, but one of the reasons why people learn calculus is because you can use calculus to find the area of weird and wild shapes. That's one of the major topics when people learn calculus, is finding the area of a weird curved shape. But anyway, for our purposes, it's not going to be such a big deal, because we are going to focus, when we do our examples, we're going to focus on just grids of points. And to find the area of a grid of points is easy. You just count up all the points in the grid, all right? When people do this in the real world, it's not so hard to use a computer to find the area. Like if you have a map of the state of Connecticut and you have each of the districts drawn in the map, you can scan the map into your computer, and your computer can compute the area without any trouble, really. So in the real world, this is not a problem. For our purposes, doing examples in a math class, this is kind of an issue, but we're gonna do all our examples on grids where it's not such a big deal. All right, so what I would like is I'm going to hand out another handout which has shapes which are based on grids, and I want us to try to compute the convex hull ratio for each of those shapes. I'm going to do the first one. You are going to do the other ones. But let me just say, on a grid, this is easy, right? Just count the grid squares. And I'll show you exactly what I mean by that. All right, let's look at the handout together. Print it out if you've got a printer. All right, so I got my grids here. We're going to try to compute the convex hull score of each one of these. Let's start off with this one here. So what you got to do is, first of all, draw the convex hull, because my goal is to compare the area of the original thing versus the area of the convex hull. So I'm considering only these black ones as the region here. I'm going to draw in the convex hull like I did before. It would look like this. I got to fill in those little inny parts, and then, going over here, fill that one in, right? Up here. Here I need to fill in from there to there, right? Here I need to fill in, I guess, from here to there, and then across here. All right. This now is the convex hull. Everything inside the red region is the convex hull. And then, of course, the original shape is just the black squares. All right. I hope that made some kind of sense. And now, what is the convex hull score? Over here, I'll do this. The convex hull score is, remember, it's the area of the original divided by the area of the convex hull. And what's that going to be? The area of the original, let me make my dots smaller. The area of the original I can do by just counting up the boxes, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23. Okay, the area of the original is 23 square whatevers, square units. So 23 up top. And on the bottom would be the area of the entire region here. Now you have to count. This can be a little difficult, but you have to count all the boxes which are enclosed in this entire convex hull region. So that, of course, does include all 23 of the original squares that I counted, but there are some white squares which are now inside the area of the convex hull, and I did count those also. So I had 23 to begin with. I'm additionally going to count the white ones. So this is 24, 25, 26, 27, 28, 29, 30, 31 whole white ones, and then some halves. And for the halves, I want you to just kind of estimate. You got to do your best to count up the halves. What did I say? That was 35? No, I lost count. Sorry, this is difficult. I had 23 of the black ones, and then 24, 29, 27, 28, 29, 30, 31, including those whole white ones, plus some halves. I'm going to go 2 halves here makes 32. 2 halves here makes 33. And then I got another half, and let's call this another 1 altogether. So this would be 34 and a half. 34 and a half. All right. You can just sort of estimate. If the picture is weirder looking, you may have to estimate the halves in a different way than I did, and that's fine as long as your count of the shapes is more or less reasonable. This is the answer though. 23 divided by 34 and a half. I did that on my calculator. You don't have to really plug this into your calculator if you don't want to, but anyway, I did. I got 0.66 repeating. All right. This is the answer. One reason that you might want to plug it into a calculator, the answer is always got to be between 0 and 1. If you get something that's more than 1, then you messed it up. Otherwise, I would not typically expect you to plug it into your calculator, but you can if you want. All right, that's the first one. See if you can do the others. Again, I will let you try to do the other ones, and I'll wait, and then we'll talk about it in a moment. All right, did you do them? I hope you did them. Let's look at this one here. I count, first of all, the area of the shape. So the convex hull score, remember, is the original area divided by the area of the convex hull. So the original area is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Divided by the convex hull area. So I have to draw the convex hull. So here it looks just like that, right? Go straight across. This is not very straight, but I mean straight across here, straight here. And then I got to connect here to there. I see one, actually this is 2 full white boxes that I enclosed here, right? 1 full one and then plus 2 halves. And then I go across there for the convex hull and then up this diagonal, right? And here, how many boxes? I'm going to call this 4 total. Actually, if you look at this whole sort of square of 8 whites that I cut in half, so it'll be 4 total. But anyway, this is my convex hull. What did I say? I had the original 13 black ones, plus additionally these white ones. These ones over here I'm going to call 2 even, and these ones over here I'm going to call 4 even. So that's a total of 6 white ones, plus the original 13 would be 19 of the white ones included, the white and the orange included in there. All right, 13 over 19, I'll plug that into my calculator also, just so we can compare it. Like I said, on a test or something, I don't care if you plug this into your calculator. I got 0.68 something, something, something. All right, so the one on the left there is 0.66. The one on the right is 0.68, suggesting that the one on the right is a little bit of a nicer shape than the one on the left. And I suppose I agree. They're both pretty weird. All right, what about this one? Did you get this one? So this one actually is already convex, right? The convex hull requires no modifications to the shape. This one is easy then. So the convex hull score in this case would be the original area, 1, 2, 3, 4, 5, 6, 7 up top, divided by the area of the convex hull, but the convex hull is the same shape, so it's 7 divided by 7, which is just 1. All right, this is the best possible value that you could get from the convex hull score. So the convex hull score of that one is 1. Excellent. How about this one? So here, the convex hull, you would draw in these guys plus 1 big diagonal like so. And what's the area of this sort of diagonal chunk here? Well, if you look at this whole square here, that's a 5 by 5 square, which would be 25. So if I cut that, half of that would be 12 and a half, I guess, white squares in there. But anyway, let's count the black ones first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. divided by, and I said the white ones that I've included there would measure 12.5. So 11 black ones plus 12.5 of the white ones makes a total of 23.5 total. All right. And what's that if I want to, just to compare with the others, I'm going to plug that into my calculator. I get 11 divided by 23.5 is 0.468 blah, 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 blah. All right. So this one is still a bit worse than the others. Remember, close to 1 is the best. Closer to 0 is the worst. This one was 0.468. I hope that's what you got, at least something close to it. Remember I said I don't really care exactly how you add up the halves, as long as it's reasonable. Okay, let's try this one. This one, I'm going to draw the convex hull is, come on now. I'm going to draw the convex hull like so. And then I got to connect this diagonal like that and this diagonal like that. So let's count the black ones first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the original area is 14 divided by that original area plus the white ones. Here I have 2 more. That's a 1 full one plus 2 halves. And then over here it looks like 1.5 more. So, sorry, that looks like 3 more to me, right? Yeah, 3 more. So, what did I say? 2 over here plus 3 more. So that's a total of 5 extra from the whites. So it's 14 over 19. And this, in my calculator, I got 0.736. All right. That's pretty good. And finally, this is a strange looking shape. All right, let's draw the convex hull here. So I'm going to have to take these like that and then cut off this corner like this. Go straight around here. Now here I'm going to have to go all the way down to this point and then go around the bend here. And then from here to make the convex hull, I got to cut up like that. All right, this one is going to be a bit of a pain, I guess, to count up all the squares, but that's how you should draw the convex hull. And so the convex hull score, I count the black ones first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 black squares. And then to count additionally the white ones, what do we got? I'll count the whole white ones. 1, 2, 3, 4 whole ones here. And then another 4.5 from there. So this this white region over here is 8.5. I'm going to write it just so I don't forget. Over here, I had 2 blocks that I cut diagonally in half. That would be 1 total block up there. And then over here, I had 1, 2, 3, 4, 5, 6 blocks that I cut diagonally in half. So this would be an area of 3 blocks. All right, I think this is accurate. Like I said before, if you get slightly different estimations of the halves, whatever, it's fine with me. So that means I had 21 total black ones, and then I'm adding in 1 makes 22, plus 3 makes 25, plus 8.5 makes 33.5. And so this value, put into my calculator, I got 0.626, blah, blah, blah. All right, I hope you got some numbers similar to those. That's what I'm sticking with. All right, that's all I wanted to say about the convex hull ratio.